you all for the 9th session of the workshop series of CIT Quantum Hackathon 2022. I'm so thrilled to welcome our dear friend Ms. Reshma as a guest speaker for our event. Hearty welcome, Reshma. She is pursuing her 5-year integrated master's in software systems at CIT. She is a quantum enthusiast and she is actively engaged herself in contributing to the Qiskit localization program. Thanks for taking your time to share your knowledge with us, ma'am. We are now ready to hear about the implementation of classical logic gates using quantum gates.
Thank you for your introduction, Dharni Prasad. So I will share my screen.
Yeah. Your screen is now visible, Reshma.
Okay, thank you. And so is my presentation visible?
Yes, it is clear.
Yeah, it's visible.
Okay, thank you. So today my topic is implementing classical gate using quantum gates. So in this session, we are going to see about a small intro on the single qubit gates, multi-qubit gates, and we'll hop on to classical how we will build a classical classical gates using quantum gates, and I will give a short tour on the IBM quantum experience, and lastly we will do a tracing of output of circuits. So first, in quantum gates, we are going to see about single qubit gates and multi-qubit gates. So, in single qubit gates, we are going to see about X, Y, Z, and Haram gate, and in multi-qubit gates, we are going to see about C naught gate, CZ, swap, C swap, and C naught gate. So, I hope everyone have watched the sessions before. I will give a small intro on these gates, so only we can build classical gates using these quantum gates. So for we have qubit 0 and 1. We know that the matrix representation for the qubit 0 will be 1 0, and for 1 it will be 0 1. And in single qubit gate, first one is an X gate, and the matrix representation of the X gate is 0 1 1 and 0. So we know that when we apply X gate for 0 we'll get 1, and for one state we'll get 0, but how we get that is here. So this is the 1 minute. um, okay, and this is the matrix representation of the X gate, and this is for 0 we have 1 and 0. So we have to do a matrix multiplication so that we'll get one state, and for one state the same process we'll multiply it with the matrix representation of 1, and so we'll get 0. And this is all about X gate. And next one is Y gate. If we apply Y gate for 0 we'll get I of one state, and for one we'll get minus I of 0. So this is the matrix representation of Y gate, that is 0 minus 1 minus I and 0. So here is how we get the we want to apply the Y gate. So this is the matrix representation of the Y gate, and this is the matrix representation of zero state. So if we multiply these two, we'll get 0 and I. So taking I outside, we'll get I of one state. And for Y also, for one state also, we'll multiply the matrix of the Y state with the one state. So we'll get minus I of 0. And hopping on to the Z gate, here Z of 0 we get 0, and Z of 1 we get minus of 1. This is the matrix representation of Z gate. So the Z will not change the state, but it changes the sign of the state for 1. So applying Z gate, Z for 0 gate, so this is the matrix representation of the Z gate, and this is the matrix representation of 0 gate, 0 state. So multiplying these two we get 1 and 0, that is 0 state. And for Z of 1, it's we are going to multiply the Z gate with the 1 state, so we'll get 0 and minus 1. So taking minus outside, we'll get minus 1 state. So next one is the Haramat gate. So hadamad of 0 we'll get plus state, and hadamad of 1 we get minus state. So this is the matrix representation of hadamad gate, that is 1 by root 2, 1, 1, 1 and minus 1. So how we are getting plus and minus gate is that we are going to see now. So uh, this is the matrix representation of Haram gate, that is here 1 by root 2 will come. So we are going to multiply the matrix of the Hadamard gate with the zeroth state. So we will get 1 by root 2 of 1 and 0. That is 50 percentage of 0 and 50 percentage of 1. So 1 by root 2 of 0 and 1. Same here, 1 by root 2 of 0. This is a minus state. And next one is multi-qubit gates. So in multi-qubit gates we have first one as CX gate. So we should consider two qubits, Q1 and Q2. So I am considering the Q1 as the control and Q2 as the target. And the rules for the CX gate is that if the control qubit is 0, the target remains unchanged, and if the control qubit is 1, and the target get flips. So here we are considering this as the control qubit, the first bit as control qubit and second bit as the target qubit. So okay, so if we consider 0 and 0, the control is also 0 and the target is also 0, then no change. When we consider 0 and 1, here also the control is 0 and there will be no change. But considering this state 1 0, here the control is 1, so we have to flip the second one. So 1 1. This is the output for this. And for considering this state 1 1, here the control is 1, so we have to flip the target. So for this the output will be 1 0. So next one is CZ gate. So in this gate, if the control qubit is 0, the target remain unchanged, the same thing. And if the control qubit is 1, the target remains the same, but the sign of the state will get flipped. So considering the 0 0, the control is 0, the target is 0, there is no change. Here also the same thing. But when we consider here, the control is also 1, the target is also 1, though so the sign will change to minus. So next one is the swap gate. So if the control is 0, then no, there will be no change, and if the control is 1, then the control and target get swapped. That is the rule. So here the control and target both are zeros, so it will remain as 0 comma 0. And here the will be get flipped, since they are not since 0 and 1, it will get two swapped, so 1 0. And if one for 1 0 it will be like 0 1, and for 1 1 it will be 1 1, since the control and target both are same. So next one is a C swap gate. Here if we have to consider three qubits, Q0, Q1 and Q2. So if Q0 is the 0, then there will be no change. But if Q0 is 1, then Q1 and Q2 will be swapped. So here considering this for these four states, the Q0 will be 0. So there will be no change in the outputs. But considering this one, the Q0 is 1. So this two will be get swapped. But since the two states are 0, we will not get any difference. But considering this state, the 101, so this is 1. So these two will get swapped. So this output will be 110. So here also the same thing, but here the since Q1 and Q2 both are 1, the swap occurs, but it will be same. So next gate is that CCX, that is controlled CX gate. So here if the rule is that if here also we want to consider three qubits, that is Q0, Q1 and Q2. So if Q0 and Q1 is 1, that Q2 will be flipped. So here for these all states, the Q0 and Q1 will not be 1, but for these two states, the Q0 Q1 both will be 1, so Q3 will be flipped. So for this state, the output will be 111. For this state, the third qubit Q3 will be flipped, so the output will be 110. So next, I'm going to explain the classical gates using how we can build classical gates using quantum gates. So for that, so actually first I am going to give a tour on the IBM Quantum Composer and IBM Quantum Lab. So this is all about the IBM Quantum experience. Here we have two sessions like IBM Quantum Composer and IBM Quantum Lab. So in this is the IBM Quantum Composer, and here we can create circuits and run them, and we can run them in real time also. So here in this screen only we will do all the operations, and here left sides the operators will be present. So we have seen some qubit gates now, that is H gate, this is X gate, this is CX, and this is CCX, this is swap gate, and this are all other gates like T gate, S gate, and Z gate, and this is used for measurement. So now I'm going to build a simple circuit. So this is a CCX, I'm going to build CCX gate. So already we have two qubits here. So here there will be a coding session, so we can do both coding and also we can do in this the drag and drop side. So if you want to add another qubit, here plus sign will be present, so we can add another qubit. So here also this is the classical bits. So we use classical bits for measurement. So first I'm going to do a small CCX gate. So okay. So the output will be displayed here itself, that is the bar graph, and the q sphere will be displayed here itself. So here we can see that since both the input are 0 for the control qubit gates, we get the output as 0 only. So here the 000 will state will be present. So if the control is 1, then we get 001. This will be flipped. So this is how we will use the quantum composer. So we can so these are all work under simulators, but if you want to submit them to a real quantum device, we have an option here like setup and run. If we click that, we have several quantum machines present, and the names which start with IBM are the quantum machines. So and also here we have simulators. These are all simulator present in the quantum composer. So the here the advantage is that we can run our own circuit in the quantum machine, real quantum IBM quantum machine. So I want to choose any one of the quantum machine. I can choose any one of the quantum machine here. So 1 minute. So it will display and the limit of the qubits. So in this quantum machine we can only send a circuit which has 7 qubit limit, and here also 7 qubit, and here it's reduced to 5 qubits. So in this quantum real time machine we can only submit circuit which are limited to 5 qubits, and here this is also 5 qubits. And this 503, 504 and all are the waiting the jobs that are submitted. I mean this 152 is already pending jobs, so if we submit the job, it will be go as 153. So okay, I will submit this circuit to this one, and we can increase the shots by increase or decrease the shots. So I'll keep the shot count as 1024, and I'll name my job as my my first circuit, and I can run. Okay, we want to measure the circuit, so Okay, we have submitted the job to this quantum machine. So, so our job is submitted to it and it's pending. So it will take some time until now, until I will show you the how to build classical gates using quantum gates. And first one is that of not gate. We know that in not gate 0 will give that output 1 and 1 will give the output 0. So here I've written a function for not gate. For building not gate, we have the same function in a quantum gate also. One gate performs as same as not gate. Can anybody say which gate performs as same as not gates in quantum gate?
Polyx.
Yeah, it's correct. So X gate. So X gate will perform as as classical NOT gate. So we can use quantum X gate to get the output for NOT gate. So first I put quantums. First we need to initialize something. There is quantum circuit and quantum registers and classical registers and all. So I have also used quasum simulator to run to get the output. So for that I've written for first not gate I've written a function which has quantum circuit of 1 comma 1. So this one is how many quantum bits we are going to initialize, and the second one is that the how many classical circuit bits we are going to initialize. So first I want to check if the input is 1. I'm going to since it is a single qubit gate, I'm going to pass a single variable, that is input. So if the input is equal to 1, then we want to change the input x qubit to 1. So that for that reason I have given this if statement. So after changing the input, then we have to do that not function. So for not we are going to put x of 0. So and then I've measured the 0th bit and I also got the output. So here I'm going to run for all the inputs. So for 0 for qubit q0, for q to 0 and q to 1, I'm going to run the circuit. So if we run not for q is equal to 0, so this is not gate, we'll get the input output as 1. So we got the output for 0 state, we'll get 1. And if we run for 1, so we'll get 0. So this is all about not gate. And next one is or gate. The function of or gate is that if both the qubits are if either one of the qubit is 1, we'll get the output as 1. So this is the function of or gate. So we need to okay, first this two ifs is for changing the qubit is to 1. So next for doing or gate, first we need to apply cx gate for control x gate for 1 and 2, and we need to apply 0 for control x gate for 0 and 1. Next we need to apply ccx, that is control x gate for 0 1 2. So I'll show here. Okay. This is the circuit for OR gate. So initially, both Q0, Q1, Q2, all the three will be in zero state. So first, I'm applying control X gate for Q1 and Q2. We know that in CX gate, if the control is 1, the target will get flipped. Okay, so 1 minute. Okay, considering this circuit, initially all the three states will be of input 0. So first we are applying cx gate. So since this initially this is control and this is target, so since the control is 0, the target have no change. So here also we will be having 0. Considering this operation, the control is 0, so the target will not get flipped. So here also will be 0 and here also will be 0. So if we apply CCX for 0 0, the target will not be changed, so here also 0. The output of the circuit will be 0. And so we'll see a circuit which gives 1. Okay, considering this circuit, the Q0 and Q1, so Q0 will be 0 and Q1 will be 0 initially, but we have applied X gate, so Q1 will be 1. And here we have done a CX gate, so if control is 1, the target will get flipped here. So since the control is 1, the target will get flipped, so here 1 will become. And considering this operation, so the control is 0, uh, so the target will get flipped. So we are having 1 here, so when 1 get flipped it will become 0. Next, considering CCX gate, we know that there will be no change if the control is 0. Q1 and Q2 is 0, so this 1 remains the same. So we measuring the Q2, we will get 1. So that's why we are getting the output as 1. So the next gate is XOR gate. So the operation of XOR is that if any of the qubit bit is 1, then we'll get the output. Not 1 second. If the two bits are different, we'll get the output as 1. If they are same, the output will be 0. So considering this, here also we will be having three qubits. So initially we have to apply CX gate for 0 and 0th qubit and second qubit, and we have to apply the CX gate for 1th qubit and second qubit. So okay, here we are having Q0 as 1 and Q1 as 0, and this will be initially 0. So if we apply CX gate, if the control qubit is 1, the target will get flipped. Considering this case, the control is 1, so the target will get flipped, so 0 will be flipped to 1. And here Q1, considering Q1, the control is 0, so target will not get flipped, so the same state will remain. So output of the circuit, this circuit will be 1. So like that, for 0 1 we'll get output 1, and for 1 0 we'll get output 1. Okay, for next one is AND gate. So for AND gate, if any one of the input is 0, then the output will be 0. So we have a similar gate in a quantum gate. With single quantum gate we can achieve this AND gate. So anybody can tell which gate will get AND gate? Anybody can guess? We have seen that gate in multi-qubit gates. Okay, I'll say it. So that is CCX gate. So here in CCX, we are going to use CCX gate. So with you only using CCX gate, we can get the AND input. So we have seen that in CCX gate, if the control and target both are 1, we'll get the output as 1. So here we are using CCX gate. So here the control and target both are 0, so we'll get 0. So the output will be 0. And for this input 0 and 1, we'll get 0 since the control and target both are not 1. So here also the same case. But here we have control target both as 1, so we'll get output as 1. So next one is Nand Gate, and it works as an opposite to AND gate. So it's very simple. We'll do a X, that is we'll perform the AND gate, and finally we'll add an X to it, so it will be the opposite for the AND gate. So here for 0 and 0 we'll get 1, and for 0 1 we'll get 1, for 1 0 also we'll get 1, but for 1 1 we'll get 0. So that's all. Anybody have a doubt in previous things? Okay, I hope everybody understood. Okay, the job is still running. We'll submit it in another one. So next one is we are going to trace the output for the circuits. So firstly, we are going to trace the output of this circuit. So initially, all the qubits will be in the state 0. So after applying Hadamat, for when we apply Hadamat for zeroth state, we'll get 50 percentage 0 and 50 percentage 1. Okay, and there is an another gate, CX gate, for Q0 and Q1. So we have to consider both 0 and 1 for this circuit. So if the output is 0, then for CX, if the control is 0, the target will be unchanged. So if the control is 0, and the target will also be 0, so it will be unchanged. And if we consider 1, so it's 0 0, we'll measure, we'll get 0 0. And next we have to consider 1. So here we have to uh, put the CX gate. So for 1 we'll get like, if the control is 1, then the target will get flipped. So the zeroth state will be flipped to 1. So the another state we'll get as output is 0 1. So output for this circuit will be both 0 0 and 0 1. So next we are going to trace output for this circuit. So here, initially all the qubits will be in the state 0, and we are going to apply Hadamat gate. So when we apply Hadamat gate, we'll get 0 or 1. So first we have to consider the zeroth output. So if the control is 0, the target remain unchanged, so 0. So considering this case, the control is 0, so the target is also 0. So the first output state will be 0 0 0. So next we are considering 1. So if the control is 1, the target will be flipped. So this state will be changed to 1. And here also, we are considering 1. If the control is 1, then the target will be changed to 1. So here the output state will be 1 1 1. And so now we are going to build a half adder circuit. So this is the classical diagram for half adder circuit. So until now, anybody have any doubts regarding the session?
I guess no, Reshma, it is clear.
Okay, I will carry on. So this is the classical circuit for half adder. So in we have to use two gates here, XOR gate and an AND gate. We have already seen how to implement XOR gate in quantum and AND gate. Um, so here this is the circuit for XOR gate, and this is the circuit for AND gate. So using these two gates, we are going to build quantum circuit for this and half adder. So for half adder, the truth table is that for 0 0 input we'll have sum 0 and carry 0. For input 0 1, sum will be 1 and carry will be 0. For input 1 0, the sum will be 1 and carry will be 0, and the input 1 and 1 will get 0 0 and 1. So we want to for building for building the quantum circuit, so we have to consider four qubits. The first For the first qubit we have to send the a, and for b we want to have another qubit q2, and we have to get both sum and carry. So for sum we are putting another qubit, and for carry we are having another qubit. So for getting sum, we have to perform XOR gate for input A and B. So this is the circuit for XOR gate. So we have to perform XOR gate for sum, calculating the sum. So here we have to put one control CX gate, and here one control CX gate. So by this doing this, we'll get the sum of these two, and to obtain the carry we have to put ccx gate for inputs and input. So here I'm going to put a ccx gate. So q1 and q2 will be the control, and this fourth bit will be the target. So by using this I've created a circuit here. So we have seen how to build the half adder. For that, first we have to do the sum part. For that I've done two cx gate for first qubit and third qubit, and second qubit and third qubit. So I'll show the circuit. Yeah, here we have in the first part we have implemented the XOR gate, and for finding the sum, and in the second part we have implemented the CCX gate for finding the carry. So when we give input 0 and 0, the carry will be 0 and the sum will also be 0. And if we give input 0 and 1, we'll get carry as 0 and sum as 1. So in quantum computing we have to read like q1 and q0, so it will be in reverse format. So we are getting 0 and 1, and adder with inputs 1 and 0 gives carry as 0 and sum as 1, and adder with inputs 1 and 1 gives carry as 1 and and sum as 0. So this is how we can build classical circuits using quantum circuits. And so the job is still in the queue. Mm. Okay, until now anybody have any doubts regarding the session, like the gates and all? Okay, we'll wait for some time. I think all the machines are very busy. So okay, actually, if the job get executed and we'll get a result from them, so in that result we'll get a transpile circuit and we also get the output for the circuit. So the reason for running the jobs in IBM Quantum machines, real-time machines, is that we'll get the exact output. So that's why we are running the this in real machines. So here also we'll get all the outputs, like we have the state probability and q sphere. So I'll show you some gates, like we have seen Z gate in while explaining. So if we apply Z gate for qubit 0, we'll get the same answer as qubit 0. But if we apply Z gate for 1, we'll get answer the same as 1, but the change is that we told that there will be a sign change. The sign change can be viewed in here. So first, when we apply Z gate, we'll get in blue color and the state will be in 0. So but after, when we apply 1, we'll get same state 1, but the color will be changed. This color change will indicate the sign is changed to negative. And we are now going to apply H gate. So I've said that when we apply a H gate, we'll get 50 percentage 0 and 50 percentage 1. So that's why in both the states the graph is shown like this. Probability is 50% here. For state 0 is also 50%. And if we apply H gate for one state 1, we'll get the same probability here, 0 and 1, but we can notice the change in here, that is the zeroth state is in blue color, that is in positive, and the one state is in red color, that indicates it is negative. So okay, I think every circle, it's all busy. So anybody have any doubt till now? That's all from my side.
Hello.
Yeah, sir.
Actually, why do we need to implement classical circuits using quantum gates and all? Is there any particular use case for it? I'm new to it, so I'm asking.
Okay, if you want, quantum is new subject now. So if you want to do a half adder, so we are going to quantum to get a fast output. So if you want to implement a half adder in quantum, we need to change it to quantum means. So only we are converting the classical gates to quantum gates.
Okay, okay, I get it.
Okay. So the time is, it's showing us 5 minutes, but okay, that's all from my side, ma'am. That's all.
I guess you have explained it pretty clear, Reshma.
Yeah, I will post this result of this thing in the Discord channel so that everybody can view.
Sure.
Okay.
It was a wonderful session, Reshma, and you have made us clear about using the IBM Quantum and Quantum Lab experience. I
Thank
guess